All right, should we get started? It's always nice seeing all of you. This is a big one. This is one of the ones I like. I sit down on my couch and talk through with my wife, try to explain this in intuitive terms, what we're doing. This is one of the big ones. You've seen the topics we've been covering in like part 3, essentially, like hypothesis testing and such. Which is all stuff you're very familiar with. You know how to run a hypothesis test, both from your stats class and in some of the ways that we're doing it in this class. And you've also seen regression. How many of you have, raise of hands here, how many of you have seen a regression done? Okay, nice, like fitting a best fit line, getting a slope and such. How many of you would feel comfortable running a regression today? Okay, so we're gonna fix this. Also, I think often when we teach regression, we don't fully talk about the intuition for what it is that the p-values are doing. So we're gonna spend a ton of time today. We have one goal for the class today. And we're essentially gonna get there by the end. It'll be like about an hour in. It's going to take us about an hour to fully finish our goal. And then we're going to run regressions, and you're going to interpret the p-values. This is something I will probably ask on a mini exam. And you're definitely going to be doing this on your homework, not just for this upcoming one, but for essentially all of them coming up in the future. What we're doing today is building the groundwork for what we do the rest of the semester. Everything else we do will be a variant on the idea we're developing today. So I'm really excited. All of part 3 was in service of doing this. So we did a bunch of work talking about simulations and hypothesis testing and such. It was all in the service of doing this. So I'm really excited for what we're doing. Before we get in, are there any housekeeping questions? Yes, Aiden. Is it not posted?
The actual file is just not like the grade submission.
Okay, interesting. Yeah, that should be posted by now. Maybe try refreshing, and if it doesn't, I'll go back and check in my office after class. Yeah, thanks. I know a lot of you are.
Yeah, never mind.
Nice, good. Okay.
An hour ago.
Yeah, it might have just not have been posted by then. Yeah. I know a lot of you use the GradeScope submission portal to answer the questions. Yeah.
The first question of homework you can't actually type in. Everything else works 2 through 5. Just the first one you can't type an answer.
Okay. So like no answer.
There's no answer box.
Okay. Yeah. Let me. I'll make a note of that and fix it after class. Thank you. Okay. What else? And I just gave you a couple of extra days to submit this. Your break just got extended a couple of days, so I hope you don't mind. Yeah, so homework 8 is posted. Also, you should have access to the slides for last class, and then also the slides for today. So those should be posted there. And then once we're done with the live stream, I'll post that on the page. Okay, so great, and then mini exam on Monday, or Tuesday, I guess in your case. If you come here on Monday, I will not be here. All right, so let's just remind ourselves a bit of where we've been. So last class on Tuesday, we talked about sort of our basic idea of a t-test. This is the example we ran with, I believe, right before spring break. We just walked through this example using, summary statistics to characterize essentially the t statistic, and then we use the t statistic with the CDF of the t distribution to give us a p-value. So we walked through this idea here. We calculated the t, and then we calculated the p-value from the t statistic using the t distribution. But this is a pretty involved approach. It turns out we have software that will allow us to solve these kinds of things much more simply. So in general, like I have never run this in my work as an economist. Like, I just don't do it this way. And so what I'm training you to do is use the tools that we actually use in the field. We have to understand what it is that we're doing when we run these things. But once we understand the process and like what's going on behind the scenes, it's much better just to use the simple tools. And so what we did is we actually constructed the same example using the raw data. So we don't actually have to construct the population statistics. We just take the data, put it into the t-test package, and then perform a t-test. So we can do all of what we did before just with one line of code that's relatively straightforward. Turns out the numbers come out to be exactly the same. And the idea here is pretty familiar, right? We have a null hypothesis, which in our wait time example was 10 minutes. And we said, okay, we have a null hypothesis. We're going to center our t-distribution around that null hypothesis and then check what the probability is that we get some sample mean as extreme as the one we see. And this is like our standard t-test approach. So we just find the p-value in the tails. So yeah, and just as a reminder, we get this t-distribution just directly from the central limit theorem. We're saying we have a known distribution of the sample means, even if we don't know the distribution of the data in the sample. An incredibly powerful result. It's like one of the big ones. And then we talked about whether we use one or two tails. We talked about why it is we use two tails essentially in every situation we encounter. So essentially, from here on out, we're going to be using two tails in every case. It's what's built into the software by default. It's what we just almost always use. And then we encountered a second type of question, which was not just whether the mean itself is 10, but are two means equal? And so you could think of like, are wait times in the morning and the afternoon different from each other? And so what we're doing today is extending this example into something a little more complicated. In some ways, it's not like so complicated, but we're going to answer a different type of question that's very similar to this example we walked through. And you're going to tell me by the end of class whether you're tired of talking about wait times. Okay, so we walked through this example. We said we have two different samples, potentially from different random variables, and we're trying to check whether the means are actually different between these two samples. And so last class we walked through this process of essentially turning a two-sample question into one that can be answered using a t-test. So we essentially constructed two data sets, two samples. We had the distribution of the actual observations. So in the morning, we have a distribution of wait times that looks like this. And in the afternoon, we have a distribution of wait times that looks like this. So just like we've talked about with data visualization, it's very nice to show the actual raw data. And then we can also show a box plot to show the different quartiles. And so we can do that for both. And then I've also on the side here plotted the sample means. So this is just the height of the sample mean. And then I have these error bars representing this the sample standard error of the data, which you can see is much tighter than the actual distribution in the raw data. And you know why this is. The standard error will always be smaller than the standard deviation of the data, because when we talk about the distribution of the sample means, the variability is much smaller. And you can see this just from the fact that we divide the standard deviation by the square root of n. So the variability in the sample mean is much smaller than the variability in the sample data. Okay, and so we asked, how do we turn this thing into a test that we're familiar with? Which is like, if you encounter a new problem in your life, try to take the new problem and make it look like a problem you're familiar with solving. This is like how we solve new problems. We take new problems, we make them look like old problems. And so what we can do here is take our new problem, turn it into we go from 2 sample into 1 sample simply by taking the difference between sample means. And this is what we did last time. A pretty powerful technique. A general solution approach technique. Turn a new problem into an old problem. And so we talked about what a distribution of sample mean differences would look like if the 2 means were the same, be centered on 0. So we talked about this thing. This is relatively intuitive that the sample mean will be centered on 0. But we were sort of left with this question of like, what's the standard error of the difference in sample means? And so we talked through some of the math for how to construct the standard error of the difference in sample means. With a single sample mean, we had this thing. So the standard deviation of the data divided by divided by n, and then we just take the square root of this thing. Where with the difference in sample means, we have to sort of add the variability in the 2 samples together, and then we take the standard deviation, or excuse me, the square root of the sum of the standard errors. So it's this thing. And you could think of this somewhat intuitively. I think we talked through some of this last time, like if there's no variability in one of the 2 samples, then you're only going to have the variability in the one sample that does have variability. And so you're not actually introducing any new variability when you subtract off some unvariable sample mean. You're going to get variability from just one of the 2 samples. And so you can see if this was 0, then the standard error of the difference in sample means would just be the variability of one of the 2 samples. Okay, so that's awfully nice. We have this combination of variability, and I think I showed this picture last time. So if we have an original sample that has a relatively tight distribution, when we take the difference in 2 samples, we actually end up with more variability in the difference of 2 samples than the original sample itself. And so this is just a picture to represent that idea. Just more variability when we take the difference. And the default null hypothesis, which we're going to keep working with today, is this thing. So we have the difference in means is equal to 0. This is just the default null. It's like the thing we're trying to test is that there's no difference. So we're coming in expecting that there is no difference. That's the default null. Okay, and so we walked through how to construct a t-test just visually. It's exactly the same as we've always done. We just check the distribution under the null hypothesis and then find the area in the tails that's at least as extreme as the sample mean that we've observed. This is all with 2 distributions that are equal. But the picture I wanted you to remember from last time was this thing. If we have 2 sample means with very different underlying distributions, then when we take the difference, that difference is not going to be centered on 0 anymore. It's going to be centered on the truth, but we don't know where the truth is. We just observe one sample mean. And then the question is how to find the p-values. So our t-distribution is centered on the null hypothesis. And then we just try to find, using a standard t-test approach, the probability of observing an event as extreme as the one that we've observed. So that looks like this. We have our null hypothesis, we center the t-distribution on the null, and then we just check the area under the tails. That's more extreme than the sample mean. Okay, so we walked through and ran a test here, found that the difference was our empirical difference between the 2 sample means was 2.05 minutes, and then the p-value was just incredibly small. So that was the thing we did last time, and I mentioned this is one of the most common types of statistical tests we do, the 2 sample t-test. But the next thing we're doing is taking this intuition and extending it into a more general environment. 2 sample t-test is one of the most common approaches, but there's a more general and more flexible approach that we're going to spend the rest of the semester talking about. Like, I'm not exaggerating. We're going to spend all of part 4, all of part 5, and then some of part 6 working with this model we're going to introduce today, which is regression, or the general linear model. And what I'm going to convince you of by the end of class today is that a t-test is just a simple form of regression. And regression actually does a t-test and does many other types of things, flexibly extending a t-test into many other types of tests we can perform. So it's very flexible. Okay, so that's where we've been. And I like to recap that to give you sort of a running start into what we're doing today. We have some intuition we're going to spend some time talking about at the beginning, which will look very familiar to a t-test. And then we're going to develop, or sort of extend that intuition into a more flexible environment. Okay, I've said that like 4 times. We ready? I need like dramatic music sometimes. This is like one of the days where I wish I had like a background soundtrack. Maybe I'll add it to the live stream after I post it. Okay, so all we're gonna do today is draw some lines. And I'm going to convince you that drawing lines will allow us to run t-tests. And we're not just gonna run t-tests on differences in means, but we're going to run t-tests on slopes as well. So we're going to build up to this. By the time we get there, it'll feel very intuitive. And you're going to be able to interpret, using English, what a p-value on a regression result means for us. I'm going to show you a bunch of pictures. We're going to do this all very intuitively today. Next time, we're going to develop the sort of more rigorous definitions. Okay, I know you want to be outside, so we're going to keep this intuitive for today. Lots of pretty pictures. So all we're going to do essentially, since basic algebra, you've been able to work with linear equations. So this is just y is equal to mx plus b. Just we have a slope, which is given to us by m, and we have an intercept given to us by b. What I'm going to convince you of by the end of the semester is that this is nearly enough to do like 95% of the statistical work we do in science. This is just a line. And this is the first part of the building blocks for today. If you wanted to be fancy, and we're going to be a little bit fancy today, you can write a linear model like this in this way. We have y subscripted with I, just to represent a particular data point. And then we have this error term at the very end. So we have a line, but when we're talking about data, we want to sort of talk about how wrong the model is. And so we use this Greek symbol epsilon to denote how wrong the model is. It's like the mismatch between our model and the actual data. And so I'm going to show you a picture of what this looks like, and we'll talk about each one of these components in the context of a scatter plot. But that's the first part of the building blocks for today. The second is what we call the mean squared error. This is basically just a way of capturing how wrong the model is on average. So mean squared error is just this error term, like how wrong the model is for a particular data point. We take that error, we square it, which then, like we've talked about with variance, when we square something, it takes away the positive and negative components. It just makes it positive. You remember that when we were talking about variance, we had like the question of whether we use a V shape or we use the square. Do you remember that? It was like at the very beginning of part 3. Those of you like glancing away may have forgotten. Take a look. We spent like like 15 minutes talking about various ways of capturing the variability in data. And one of the ways was using the absolute value operator. The other was using the square function. This is just the square function. So we're just applying a square to this so that all positive and negative errors are counted equally. So it doesn't matter which way we're wrong. And then we're just taking the average of them over all of our data. Okay, so before we start talking about the possibility of slopes in this line, we're going to start with the simplest possible linear model, which is just an intercept. So we're going to spend like 20 minutes here talking about models with just an intercept. We're going to talk about the variability and how we might think about performing tests on just an intercept. So here we have the simplest model, and let's say it looks like this. So we have the equation for a line, that's just a horizontal intercept. So it just runs through the intercept on the vertical axis and then doesn't do anything fancy. So the question we're going to try to answer is, first off, how do we pick what B should be? So where on the vertical line, on the vertical intercept, should we intersect the line? So where is the vertical intercept? So here I have the raw data, and this data is representing it's like paired wait time differences. So I take one customer in the morning, I take one customer in the afternoon, I take their wait times, and then I subtract them from each other. So this is still a one sample t-test, or one sample. We're not taking the difference between sample means, but all we're doing is comparing wait times in the morning and afternoon, sort of pairwise. So this is our raw data. So then I have two examples here, two different choices of B. The first one is pretty high, so it's B is equal to 2.5. And you can see a couple of things here. So first off, this first data point, when we choose a very high value of B, I have the data point represented in blue. I have the B, so the choice of the line, represented in red. And then I have the error term represented with this green dashed line. This green dashed line is just that epsilon term we were introducing before, just the error. And when we choose a very high value of B, the error is very large because we're sort of pretty far away from the data point. The second data point, which I can't reach to, is very small when we have B equal 2.5. But if we lower B, we move much closer to this first data point. So we've lowered B. The error for the first data point is very small, but the error for the second data point is very big. So you can see, like, moving B around changes the error, which also changes the mean squared error, right? Because we're just going through, adding up each of the individual lines, squaring them, and then taking the average of them. That's just our mean squared error. And what I'm going to show you is that the mean squared error in this model, in a certain circumstance, is equal to the variance. Okay, so let's say my goal is to minimize the mean squared error. This is truly a question for you, and you're going to be able to answer this. If I were trying to minimize the mean squared error, how should I choose B? Some guesses. Luke.
Either the median or the mean.
So Luke is putting out two proposals. The first one is the median. So picking B at the exact middle point of the data, according to the median. And the other is the mean. So we go through, we add up all of the different data points, and we take the weighted average. I'm going to put this to a vote. No abstentions. All right, so how many of you think, it is one of these two answers. How many of you think the choice of B equal to the median will minimize the mean squared errors? And how many of you think setting b equal to the mean will minimize mean squared errors? So median, raise your hand. You can raise, like, this is a chance to be wrong with no penalty. It's a good opportunity. Also, like, high risk, high reward. Okay. How many of you think it's mean? Nice. Someone want to tell me why you think it's the mean? Yeah.
It's the average score, and most of the data points are going to be likely to lie there. So
Yeah, so mean is like a pretty natural way of capturing like average distance. I would say median is also a pretty natural way of capturing distances. But maybe like we sort of teed up at the very beginning of part 3, like mean is just kind of a more natural approach. So yeah, Luke.
It's also more influenced by like outliers as well, so it can take account for that as well.
Yeah, this is a really interesting insight. So the mean is actually more responsive to outliers. And intuitively, you can see mean squared error is also very responsive to outliers. So if we have a very large number, a very large error, because we're squaring it, we want to be very responsive to outliers. So the answer here is the mean. And what I'm going to show you is a picture of the mean squared error according to our choice of b. So I've plotted all of the data points. I've plotted the mean. So b is equal to the mean. So this is just a line with a vertical intercept that runs exactly through the mean. And I guess I forgot to mention this. The horizontal axis with these data points is meaningless. I'm just basically jittering them, just so we can see all the different data points. But the horizontal axis doesn't mean anything here, and so I haven't even included it. So we're just running a line through all of our data points at exactly the mean. And in this second figure, what I've done is plotted all of the different possible choices, or like a bunch of different choices of b. And on the vertical axis, I'm showing the mean squared error at each one of those choices of b. So, and this bottom point is exactly the mean. So as we move away from the mean squared error actually goes up. So our goal, not just with the single intercept model, but also with all of our models upcoming, is to find this minimum point. We're trying to minimize the mean squared error. This is just a picture showing it. Okay, any questions here? Nice. All right, so we have mean squared error. We're choosing a vertical intercept that's equal to the mean, which minimizes the mean squared error. And it turns out when we have a single intercept model where all we're picking is b, the mean squared error at the minimum of mean squared error is equal to the variance. If you think back to our definition of what variance is, it turns out all we're doing is we're taking the variability in the data, we're taking each data point, subtracting off the mean, and then taking the square of that thing, and then just taking the average. That's variance, and it turns out that's exactly equal to mean squared error with the intercept model. So mean squared error in this case is the same thing as variance. But you'll remember, this is, yeah?
is that only the case when it's a constant on the y-axis?
Yes. Yeah, great observation. So I'll talk about this a little bit later, but as soon as we start adding slopes, then the vertical intercept no longer becomes the mean. Yeah, and I'll show you an example of how this works later. Yeah, great observation. So here, you'll remember, this is just a sample, right? I've just taken a sample of 30 differences in wait times between the morning and afternoon. And you'll remember from sampling error, every time we do this, we get a slightly different sample. So there's like variability in the sample itself. This next picture, I've taken 8 different samples from this sampling distribution and fitted 8 separate models to each one of these separate samples. And a couple of things to note here. The big reason we're doing this is just to show that, again, when we're running a model like this, fitting lines, we're still getting sampling error. So just like we did before, taking a sample mean, when we're fitting a sample with a line, we get variability in the data and in the model. And then also, you can see, just like before, when we're talking about t-tests, and if this is feeling familiar to you, that's on purpose. This is exactly the same type of thing we've been doing, just from a different perspective. Here, each time we run a fitted model on each one of these samples, we get a slightly different mean. So we're getting variation in the sample mean, which should remind you of the central limit theorem. So variability here. And so what I've done here is just printed out the model itself, the errors with the data, and then I've also included the mean with each one of these samples. And so you can see there's sampling variation in the data. So just like before, sampling error just due to the randomness of drawing from a random variable. Okay, so legit question for you. Let's say, I'm looking for an answer. Let's say I take each one of these B's, right? We've gone through, we've picked a B for each one of these samples. Let's say I do this 1,000 times. And on the horizontal axis, I plot a histogram of the B's, our fitted model with 1,000 different samples. If you were to take a guess, what would that histogram look like? What type of distribution? Yeah, Luke. So Luke is saying it might look approximately normal. What about some other answers? How many of you think it might look approximately normal? Okay. How many think it will not look approximately normal? Do you know the YouTube channel Very Normal? It's about statistics. No one? Okay. Maybe just me. I watch a lot of their content. It's good statistics stuff. Yeah, so it's going to look approximately normal. It's going to look like this. So on the horizontal axis, I've just, I've run 1,000 samples. I've fitted each one of these samples with a intercept model, so a choice of B, and then I've plotted a histogram over all of the B's. And then on top of that, I've plotted a t-distribution just to show that it's consistent. So does this look familiar? I think this is like exactly the same picture I've drawn in the last 3 classes. This is on purpose. If this looks familiar, you're on the right track. Or at least we're doing our job in this room. So we have a distribution of B's. This is the intercept coefficient, which we're calling B. If I were to ask you what the probability of the intercept being 0 would be, how would you go about answering this question? The probability that the intercept is 0. I'm legit looking for an answer here, but not just from Luke. How would we find, it doesn't have to be a number, just a process. How do we find the probability of seeing an event as extreme as 0? I see a bunch of hand movements that are indicating, yeah, Drew.
Find the area of the curve where the intercept parameter is 0.
Yeah, so find the area under this curve where the intercept parameter is 0. This is a t-test, right? So if we're trying to test whether the intercept is equal to some value, like our null hypothesis, intercept being 0, all we have to do is perform a t-test on the coefficient itself. This is a t-test. And this is exactly the same t-test as we've done before. We're just performing a t-test on the means. Is the mean of our data the true underlying parameter? What's the probability that it's as extreme as 0? That's a t-test. So the point of this slide is to show you like the connection between what we're doing with drawing lines to what we've done with a t-test. Okay, so when we take a sample from our distribution, we're not guaranteed for it to be exactly equal to the middle of our sampling distribution. So here, if we were to draw a sample, which I've done here, it could be very different from the center of the underlying distribution. So let's say our sample mean is 1.97, and we ask this question, which I just did. You can see it's probably going to be roughly 0. Like the probability of seeing something as extreme as 0 is near 0. It's not ever going to be exactly equal to 0, but it's going to be very close. So the way we perform this t-test is like we always do. We can center, or I guess it's mathematically equivalent to what we did last class. We can center the t-distribution on our sample mean and then check in the tails for something as extreme as 0. So here I have one observation, one sample mean, one sample B, the vertical intercept. And then I've centered the t-distribution on that mean, on that B parameter, just right around, just under 2. And then we can find the area under the tails more extreme than 0, and then something equally extreme on the other side. And this is going to be 0. So this is, how we perform t-tests. And everything we've just done drawing an intercept-only model is exactly equal to what we've done with t-tests. Are you amazed? To quote, what's the movie 300? Or, no, wait, hold on. Never mind. I'm bad with movie quotes. Don't, Gladiator. Are you not entertained? Yes, thank you. See, I learned something from you too. Okay, so very nice. This is frankly amazing. If I were to stop here, I hope you would feel that this is amazing. We have a line that we're drawing through our data, capturing the mean. This is all we're doing is minimizing the error in our data. The error in our model relative to the data, minimizing that gives us a distribution that we can then deal with using the central limit theorem. Amazing. But we're going to take this much further. This is just the starting point. So this is our regression model. We just have a horizontal line. This is just a summary. This is some of the notation we're going to be using. So we've picked B. I'm going to call this from now on beta 0. This is just standard notation for what we're doing with lines. The 0 is there to denote that it's just the intercept. It's like the simplest thing. The beta is just a B, but fancier. For some reason, we like to use fancy Greek letters. And then epsilon is the error. So we have a bunch of y's. So each one of these blue points is our y. We have beta 0, which is the intercept for this line, no slope. And then the error is just the green line. So we have each one of the 3 parts of our model captured with this picture. And just as a summary, we're saying beta 0, when we fit the model, minimizes the sum of squared errors. And the p-value tells us the probability of getting the data given our default null. From here on out, we're going to use a default null, which is that the parameter itself is equal to 0. That's going to be our default null. Okay. And then it turns out our best guess, the way we interpret this, is our best guess of the truth is this beta 0. So if I were to guess the difference in wait times in the morning and afternoon, I would guess the parameter we found for beta 0, which in this case, I think the number was 1.97. Okay. This is the simple form. What we're about to do is introduce a very similar idea, but make it more complicated. And this is truly where the power of this model starts appearing. You've seen this before. We're going to run a regression, and we're going to do this in code in a way that is accessible. So you're going to be able to do this in your final project. And a lot of you are going to be able to are going to do this in your final projects. Okay, so let's run a quick example, and then we're going to get into the slope model. We're going to not just talk about an intercept, but also talk about a slope. Okay, so we'll jump over to Colab and open the part 4.2. So here I have the imports, and you have access to these slides. So feel free to work along. So we're going to load the imports, and then I have this data set, which you can find. So here, these are, like I mentioned earlier, these are paired differences. So it's like I have a wait time in the morning and then a wait time in the afternoon. And I'm just comparing two individuals taking their difference. And I've done this 30 times. So each one of these represents a wait time difference. And then the second thing, so this is our y variable. When we run a regression, we need an x variable. For the intercept, we always use 1. So what this does is we're just multiplying the beta 0 by 1. So all we're going to get is beta 0 back. So if we multiply something by 1, then we just get the thing back. So we have a bunch of 1s here, and we just need it to be the same length as the y variable. So here, we're just going to show this data. And then all we're going to do is run this model. So you can copy this over if you'd like. But all I'm doing is I'm loading the stats modules API package. And just like my friends in college called me Little Tay, you can call this SM instead of stats modules.api. Just makes your life a lot simpler. OLS is just ordinary least squares. It's just another term for this idea of minimizing the squared errors. Least squares just comes from that idea exactly. We're squaring the errors and trying to minimize them. And then we're going to put in our y variable. So this is all of the data itself, the paired differences. And then we're going to put in our x variable, which in this case is just 1s. It's just the 1 we're multiplying by the beta 0. So it's just our constant term. So that's our model, and then we're just going to apply this fit operation to it to actually minimize the sum of squared errors. And that's going to give us a model. So we'll call this model. And then this is just sort of fancy for taking the model and giving us a nice summary. So you can just copy that. I never remember exactly how to write that, and neither should you. So you can just copy what I've done. Okay, so we'll run this, which fits the model and gives us an output of the model fit. And I'm going to make a bet with you. Maybe this isn't a very fair bet. I'm betting the credibility of the rest of the semester on the outputs of these things we're doing. We're first going to do this with a regression. We're going to test this model and find the p-values and the t-statistics using a linear regression like this. And then we're going to do it the old way, using a t-test. I'm going to bet the credibility of this semester on these two numbers being equal. I'm telling you that OLS, or regression, the general linear model, will give us exactly the same results. Okay, so let's just look at the results from the regression. So this constant, this is just representing the fact that we're only using an intercept. And then this, the rest of this row just represents all of the different values for that coefficient. So this is our B coefficient. The coefficient value is 2.04 or 2.05. So just our estimate for the difference in wait times in the morning and afternoon. We have our standard error, so this is nice. We don't have to do any work and we get a standard error, just prints it out for us. We get a t statistic, so this is telling us that our observation is roughly 23 standard errors away from our null hypothesis, which in this case is 0. So 23 standard errors away from our null. And then we get a p-value. So I'm going to ask you to interpret a p-value in a second. I'm going to interpret this one, and then you're going to interpret it later in a different context. But then we also get a 95% confidence interval. And we get all of this for free. Just the software does it for us. We don't have to do any true work. Okay, so what this p-value is telling us, this is a great exam question. Actually, I want to pause here. I want you to write on a piece of paper or in your notes in some way what this p-value is telling us. We've done a bunch of work. We've interpreted the model itself. We've run a fitting of the model, and it gives us a p-value and a coefficient. I want you to write on a piece of paper what this p-value means in English. We can do all this stuff. Lots of people can run regressions, but the key skill is being able to interpret what the regression is telling us in a correct and meaningful way. It's a big part of what we're doing. So we'll take maybe a minute here. Write it down and then check with someone next to you. All right. Someone want to tell me what this p-value means? Yeah.
Under the null, we see something as extreme as x bar about 0%.
Very nice. Perfect interpretation. We're saying under the null hypothesis, we're going to see something as extreme as our observation from our sample, roughly 0% of the time. So one way of interpreting this, maybe a little bit further, is to say, like, it's very unlikely that what we're seeing is coming from the null. So unlikely the null is true. Yeah, very nice. Any questions here? So should we run this using a one sample t-test like we've done before? Making a big bet here. Doing this live. So we have a one sample t-test. We have our null hypothesis equal to 0. We're going to put in our data, which is our y variable, and then we're going to print out the p-values and t-stats. If this isn't equal to the regression model, then we go home. How about? For the rest of the semester. All right, so we'll run this, and then we'll look at these numbers. So are these the same? Different answer. Someone answered differently. That's wrong. Yeah, so these are the same. we've rounded to 3 decimal places for the statistic, which is the same as this. And then we've also rounded this to 3 decimal places for the p-value. But you can see this number is 0 point, and then 20 zeros, and then 19. So it's 0. Okay. So I just want to pause here for a second and remind ourselves what we just did. Instead of running a t-test where we think about the sample means, we're looking at a horizontal line through our data with no meaningful x variable and performing a minimization of the error term, squared error. And then looking at the variability given to us by the central limit theorem in that parameter b. And then performing the same type of t-test, but on that parameter b. And that gives us the same numbers. And this should really be no surprise. So it's like amazing, but it's also not really that surprising true. Say that again. That's the t statistic. So that's like the number of standard errors away from separating the mean and the null. So we used this. So we calculated a t statistic at the very beginning of class last time. Here, this is like the t statistic. And you can take a look at the slides if you want. We haven't spent a lot of time talking about the t statistic, but it's essentially just a normalization of the variability in the data and the difference between the sample mean and the null. Yeah, good. What else? Okay, so I promised an extension of this. This is the basic idea. We can take a linear model, whatever that thing is, whatever the line represents, take the parameter and talk about the variability within that parameter coming from our sample. All we've done, though, is look at an intercept-only model. But what I'm going to show you is something a little more complicated. So here, I have a bunch of data. Instead of separating wait times into morning and afternoon, and then taking the difference between those two things, here I'm just plotting the wait time at a bunch of different times throughout the day. So on the horizontal axis, this is roughly like time of day, or like minutes after open. So how long did the transaction happen after the shop had opened? And then on the vertical axis, I have the wait time. So what we did in the 2-sample t-test example is take times from the afternoon, bin them all together, call that afternoon wait times, and then times from the morning, bin them all together and call those morning wait times. But it's more accurate to just represent them throughout the day. So this is like 2 dimensions of data, and we just plot this with a scatter plot. Does this look like there's a trend? Yeah. We could test whether the morning is different from the afternoon using a 2-sample t-test if we like. And we'll do this again. We did this last class, and we're going to do it again next class in a different way. But we could just test directly whether there's a relationship between between minute in the day and wait time. So first thing I'm going to do is just draw a line through this data to get the intercept-only model. So this is just, if we wanted to get the mean wait time, we could just run a line and get the intercept only. And you can see I've drawn the error for each one of these data points coming from our model. The important thing here is I've also printed out the mean squared error. So this is like how good the model is using just the intercept. But you may have noticed that you did notice that there's a trend. So what I'm going to do is include the possibility not just of controlling up and down, but also controlling the slope of this model. So we're going to introduce a second coefficient, a second parameter in our model, which controls the slope. And this is what that model looks like. And a couple of things to point out here. So I've introduced the possibility of beta 1 not being equal to 0. where with the intercept-only model, we're enforcing that it is 0. And a couple of things to notice here. First, the fact that we're including a slope in this model makes the mean squared error smaller. So our model is less wrong when we introduce a slope. You can see the mean squared error went from 6.26 to 3.25. So when there's an underlying relationship in the data, adding a slope coefficient improves the fit of our model. So our model is better. And the other thing to notice is that the intercept is no longer the mean. So as we were talking about earlier, when we introduce a slope into this thing, the intercept no longer is necessarily the mean. What the vertical intercept tells us is, in this example, it's when the coffee shop or when the shop opens directly, how long do you have to wait if you order right at open? It's like the value at an x value of 0, the wait time at open. So that's represented here. So the intercept is no longer the mean, and this beta 1 gives us something like a best guess of our relationship between minutes after open and wait time. So how much does an extra minute add to our wait time? So you wait a minute to order, how long does that add to your wait time? Okay, so this is really powerful, and we've been in this world of testing means, thinking about the sampling variation in the data, but simply thinking about the means. What I'm going to do next is show you a bunch of, so this is just one sample, right? We have 60 observations here, but you'll remember that we have sampling variability in whenever we take a sample. So every time we take a sample, the data looks slightly different. And in the past, that's been variability in the sample mean. But here, I'm going to show you there's also variability in the slope. So here's a picture of the sampling variability with the slope. Okay. Anyone see where we're going with this? This is the same picture as before, except instead of looking at just the intercept model, we're now also looking at the variability in the slope of the relationship between our data points. So I've run 8 different samples here. I've fitted each one of these models. We have the mean squared error being minimized in each one of these examples, in each one of these samples. And you can see I've plotted the slope for each one of these samples above the scatter plot. As you can see, the slope is going to be slightly different in each one of these examples. So if I were to look at this picture and I were to say, there's a slope here, certainly in our data, there's a relationship between wait time and minutes after open. But if I were to ask you this last question, could this slope that we're observing, which is given to us here, could that be due simply to random variation in the data? So sampling error. What would you say? Could this slope be due to sampling error? Could it be that we've just simply drawn a bad sample? Or like a misleading sample? Corin?
Theoretically, yes, but it's very, very unlikely.
Okay, and why do we believe it's unlikely?
Well, it has to do with the size of our sample and the standard error model.
Okay, so we need some idea, what Corin's hinting at here is we need some idea of the sort of variability of the slope, and then we need like a standard error around the slope coefficient to give us some idea of like how likely it is we could see no slope. Does this sound like a t-test? Okay. So sort of upon Corin's recommendation, what I'm going to do is take the slope from a bunch of fitted models like this. I'm going to run this 1,000 times, and then we're going to plot a histogram of that beta 1 coefficient across the slope coefficient across each one of these 1,000 samples. Anyone have an idea of what this distribution looks like? It's a histogram, a bunch of slopes across 1,000 observations, 1,000 samples. What does that histogram look like? Anyone notice the similarities? Okay. Yeah. Someone want to make a guess?
What, like what the histogram would be?
Yeah. What does that distribution look like?
On
On a limb. Someone want to go on a different limb or similar limb? Someone else want to go out on a limb here? Yeah, Ben.
just upward trending differences.
So we're going to see definitely positive relationships. I mean, we see it 8 times, so we'll probably see a lot of positive relationships. But what is the distribution of the slope parameter? So this is, this is a number. This is another number. We're just going to take a histogram of all of those numbers. What does that look like? Got one suggestion, normal. I want someone to slightly refine this a little bit. Luke. Approximately normal. Anyone noticing a pattern here? This is what it looks like. I've taken 1,000 samples. I've constructed a slope, minimizing this mean squared error. I've controlled both the intercept and the slope. And then I've plotted just the slope coefficients. And it looks like this. So this is the truth, somewhere in the middle. And then a bunch of observations, and then it gives us roughly a t distribution, which is, with a sample size of 60 like this is going to be a normal distribution. But to be more precise about it, it's approximately normal. Okay. This is where we have a background soundtrack. Like the music is like slowly picking up. Here we have a distribution of the slope coefficients, which is approximately normal. So if I were to ask you this second question, how would we test whether the slope is actually equal to 0? Like, what's the process we would follow to be able to do this? Someone help me out here. I've given you a bit of a clue on the screen. And it can't be Luke. Respect, appreciate someone else. What's the process we follow to test whether the slope is actually equal to 0? Like, no relationship between the two variables. Can I get a temperature check? I'm having some difficulty reading you. 3, like this is obvious. 2, this is like I can make it work. And 1, I'm totally lost. Can I get a temperature check? Nice, love that. That's my favorite answer. Okay, someone help me out here. What is it that we do? What's the process, the procedure we follow to test whether the slope is 0? Drew. So we'd love to find a p-value. And how do we find a p-value here? So Drew is suggesting we find a p-value, just like we do with a t-test. How would we perform a t-test, essentially, on this slope? Let's draw one sample. Remember, this is 1,000. Let's draw one. And then let's find, we know what the distribution will be. It's just the standard error of this. And then we'll find the area under the curve as extreme as 0. So I'm going to draw one sample, which turns out to be, on one side of the center of the sampling distribution. I'm going to center the t distribution on that sample, and then I'm going to find the area under the curve as extreme as 0. We don't actually see the sampling distribution, that like those 1,000 observations I drew. So what I've done is sort of hide them a little bit. All we see is just the one that we've drawn. We centered the t distribution on that sample, and then we pick, we find the area under the curve to get us a p-value, just like Drew's recommending. This allows us to find the probability that we observe a slope as steep as the one we do if there is no slope at all. What does this number look like, the p-value? If you were to just like interpret this figure. Yeah, Luke.
Very, very, very small.
Yeah, basically 0. Yeah. It's never going to be exactly 0, but it will be basically 0. Okay, I think we have just enough time. We're going to actually run this in Python. I know you were antsy to get outside and get some sunlight, but we're going to do this in code. Okay, so let's actually jump over to, so we'll copy over this stuff, jump over to our example here. You'll remember pandas. Can I actually take another temperature check on you? 3 if Python is feeling very easy. 2 if you're like able to make it through, but it's some work for you. And then 1 if you're totally lost. Love that. Okay, nice. That's where we want to be. Okay, so we're just going to import all this stuff. Pandas, you'll remember, is not the charismatic megafauna my ecology professor liked to talk about. It's the panel data set Python package. We have our stats modules API, and then NumPy is just the numbers Python package. And then what I'm going to do also is load some of this data. So minutes after open. So I'm just going to paste this in, run this, and then we also have our wait time data, which I've pasted in here. And then the last thing we're going to do is add an intercept. So we have the x variable, which is our the horizontal axis, our minutes after open. We have our y variable, which is our wait times, but then we also need an intercept. So I'm just going to add an intercept here. So we just need the ones to be exactly the same length as wait times. And then we're going to turn all of this into a data frame. So this is just a pandas data frame. It makes our data look like an Excel spreadsheet, which has a lot of handy features. So just run this. So if we were to just print this out, this looks like the following. So we have minutes after open. So this is how long the shop has been open. We have wait times, so how long the customer had to wait to get their order. And then we just have an intercept, which is just a list of ones. So we're just multiplying the beta 0, the intercept term, by 1. That's all we're doing here. Okay, and then the last step, which is really just 2 lines of code, well, sort of. We're going to try to predict wait times using time of day. So I'm going to copy this over. We're going to turn our we're going to construct an x and a y variable. So this is, we have minutes after open, and then we have intercept to be our y. So we have both the intercept term and our beta 1 term, our x variable. Yeah. So this is just np, and then we're just going to create a list of ones that's equal to the length of wait time data. So I'm going to run this, we have our x variable, which is actually 2 columns, and then our y variable, which is just the one column for wait times. And then we're going to fit this regression. So we're going to, just like we did before, we're going to put the y variable in first, x variable in second, and then we're going to fit this thing. And then we're just going to print out the model summary. Okay, and this is where I need someone in this room to interpret what we're finding. Okay, so first, someone interpret the intercept. What do these values mean? We have an intercept and a bunch of stuff. Someone interpret the coefficient and the p-value. Are y'all gonna let Luke answer? Someone else. I feel so rude when I do this. I'm sure your answer's great. Someone else. Yeah.
Under the null hypothesis, we're going to see something as extreme 0 of time.
Okay, so that's what our p-value is telling us here. Like basically, we don't see that the weight, the intercept coefficient will be 0. It's very different from 0. Someone follow this up. What does this number mean? Yeah, Luke.
Does it mean like we're 4.73 like standard errors away from the sample intercept?
So that would be the t-value.
Oh, wait.
So the t-statistic tells us how many standard errors separate our null hypothesis and our sample. Corin.
If our minutes after open is just 0, then the value of the number is going to be 0.
Potentially. I'm not entirely sure how to. I don't know that I understand what that means.
We just have the value next to our intercept for the minutes after open is just 0, then it just makes everything else 0 except the intercept, so it just gives us the value of the intercept.
Yeah, so this is just the value of the intercept. Yeah, that's, if I'm interpreting what you're saying, that's what this
So
number
that
is.
would be the model's output if minutes after open is just equal to 0. Since it's done with
Oh, yes, totally. Yeah, yeah. So what Corin is saying is like, when minutes after open is 0, the intercept gives us just the number of minutes we wait at that time of day. So this intercept is actually just telling us how many minutes you would have to wait if you ordered directly at open. So if you put in the order right as the shop is opening, you're going to wait 4.7 minutes. That's what the intercept is telling us. Okay, so that's maybe the hardest one. Someone answer this line. What is this line telling us? Primarily the coefficient and the p-value. This is a great exam question. Like, I have something almost identical to this on the homework, and you can expect something very similar to this on a mini exam. Maybe my new rule is you can't answer 2 questions. We've like a minute left in class. I want to get this done before we leave. Someone take an attempt at this. This isn't a trivial thing to do. In fact, this is one of the hardest things to do with regression, is take a regression output and interpret it. Okay, maybe I'll do it. Or Luke, did you want to take an attempt?
So the 0.079 is at the slope of the regression line,
So this is the slope of the regression line.
and then there's like a pretty much 0% chance that we would see a value as extreme as the line.
Under the null hypothesis. Yeah. So if there is no slope in reality, we would see an event as extreme as the one we do 0% of the time. So we can confidently state that there's that this is not due to chance under the null hypothesis. And what this number is telling us is that is that an answer?
Is it for like as every minute after open 0.0099 increase?
Yeah. Yeah, very nice. So the claim here with this slope is that every minute we wait after open, we are increasing our wait time for our order by 0.0 roughly 1 minutes longer. So our wait time gets longer by 0.01 minutes every minute we wait after open. Okay, so can I have like 30 seconds here? I know I'm running over. I'll give it back to you next class. This is incredible what we've done. We've taken we've spent like all of part 3 building up the apparatus to talk about hypothesis testing using t-tests. And what we've done here is talked about the variability in the parameters of a linear model in the same way that we've done with a t-test. And in fact, a linear model with just an intercept is exactly the same thing as a t-test. But we can also extend this idea of a t-test into more complicated models. So we're going to talk about using these coefficients, the distributions of these coefficients, to talk about linear models. And this is essentially what we're going to be doing the rest of the semester. Various ways of building linear models like this. You're going to see some of this on your homework, and you're going to see a lot of it on the upcoming mini exam. I have office hours directly after class. See some of you there. See the rest of you in the sunlight.